Okay, the next lecture is about time series analysis. So let's start by defining a time series. And all it is an ordered sequence of values of a variable at equally spaced time intervals. And there are 4 examples shown here. And they all demonstrate characteristics that we're going to talk about throughout the rest of this lecture. But they're all visually very distinctive, right? You can describe them in terms of how they change over time, over the long run, how they change at a high frequency, so how they change year to year, whether you can recognize patterns, whether you can recognize noise or other random elements that we can't describe using a nice trend. So for our purposes, the discussion of time series analysis is going to be, and its use in the energy industry has some things in common with topics we've already gone over, like the discussion of probability and regression. Time series in general, we're often going to use statistical moments, right? So mean and standard deviation, to describe different properties of time series. However, a key difference between what we're talking about time series and then probability is that in many cases time series can exhibit means and variance or standard deviation that change over time. And that's what makes them a little more complicated to deal with than just randomly sampling from a distribution. So here's an illustration of that. In this case, we have something that demonstrates a very periodic change, right? That it's sinusoidal. But we also notice that there's a linear trend at work too, right? So the mean of this process, the process is black, and red is indicating the average of the mean. The mean is changing, right? And we could think about all sorts of examples of things that do this over time, where there's some periodic effects, but overall something's going down or something's going up. But one thing you do notice is that the standard deviation, in other words, the oscillation around this mean red trend, is roughly normal, right? Or roughly consistent over time, right? So things aren't getting more or less volatile as you move through. The only thing that's changing here is the underlying mean trend. And this is sort of the opposite. Instead of having a changing mean and a constant standard deviation, here we have a constant mean and a changing standard deviation. These are NASDAQ daily returns, so day-to-day changes in the value of NASDAQ. And so some days it goes up, some days it goes down. Overall, if we track this over a very long period of time, we might end up at the same place where we started, but over that course of time, you're going up and down a lot. And one thing you notice here is that there are certain periods that are marked by really, really high volatility, right? So you have one day it goes way up and one day it goes way down, right? And you can imagine what, just from reading the news, that a lot of those periods of high volatility come around market scares or Fed reports that come out that get everybody worried and everybody's buying and selling stuff all in a hurry. And then there are other periods where not much happens, that increases and decreases happen, but they're not moving around the mean to the same degree. So what's the main difference between a time series and then just a sample of observations of a random variable with a known mean and standard deviation? So we've talked about a little bit about Monte Carlo simulation. And so that's sort of what I'm asking, is what's the difference between a time series and Monte Carlo simulation, where you're just reaching into a hat and the hat is described by some sort of probability distribution with a known mean and variance, and you're pulling out marbles or whatever. So on the left-hand side, we have a time series, right? And on the right-hand side, we have a distribution. And it's possible that we could put all those data points from the left-hand time series into a pile, and we could fit through maximum likelihood estimation, a probability distribution to all those data points. And it might look exactly like the probability distribution on the right, but the question is, does that mean that randomly sampling from the distribution on the right, even though it does characterize over time the probability of getting any one of those points, if we just randomly sample it, will that give us a time series that looks something like what we have on the left? And the answer is no, and we'll talk about why. So the answer is no, especially if the value of this process, x, at any one given point of time depends in any way on the value of x in the time period before or the time period before that. So I'm pointing that out here. There are red arrows pointing to sequences of dots that look like they might be somewhat related, right? So you don't have a trend overall, right? You have a process that in general is centered around, it looks like, 10 or 12 or something in between. But you do have these periods of time where the process seems to show some sort of pattern, like 5 or 6 data points in a row where it's going up, or 5 or 6 data points in a row where it's going down, and then it might switch. And these are hints of what we call memory in a time series, right? So the trends tend to persist within a time series, but overall, there's no overall trend. And another word we use for this is autocorrelation. So we'll get to autocorrelation and memory in just a minute. I want to go back and talk a little bit more about how time series analysis is similar to another topic we've already gone over, which is regression, right? We talked about how probability can be used to describe points in a time series. Like a time series might have a mean and a variance associated with it, but it's not the exact same thing as Monte Carlo simulation because of memory. It's also a little bit like regression in the fact that often we use time series analysis to identify underlying trends the same way we would with regression and patterns, to describe them mathematically, and ultimately what we're after is making some sort of prediction or forecast about what's going to happen next. We've already talked about how regression can be used in modeling electricity demand, whether that is as a function of weather or degree days within years, or year on year as a function of economic growth, changes in technology, population growth, stuff like that. And here's an example, right? So this is a time series for sure, but you can also sort of understand just visually looking at this why regression would be useful as well, because this is more or less what we did on the last tasks. We took a time series of electricity demand and other data and tried to pull out a model of electricity demand as a function of all those different data points, which we understood to be changing through time, like economic growth or population growth or weather or something like that. And clearly there's an underlying linear trend here which we could model using linear regression, where the mean is changing year to year at about the same rate, but within year there's a very constant sinusoidal pattern. So here's the key difference between time series analysis and regression. This is the equation for regression, where you have a dependent variable y and you're modeling the behavior of that dependent variable y, and it could be electricity demand or something else, based on all these other underlying independent variables, x's, and the point of regression is to find the values of b that when you put in the variable of x gives you the closest possible answer to the real value of y. Now, time series modeling allows you to replicate all of these individual processes or like for example, electricity demand, into a combination of signals. That could be year-on-year electricity growth and demand. You could have a separate seasonal variability, a separate signal for seasonal variability, and then you might have some randomness or noise in the process as well that just adds some small amount of uncertainty, and you can perfectly model the characteristics, and in some cases make a forecast and predict the value of this underlying process Y without deterministically modeling each underlying independent variable, right? So you sort of throw out the window anything you're trying to glean from GDP growth or population growth or anything like that, and all that gets translated into a mean trend or a nonlinear, a trend in the mean or a trend in the variance or something like that. And we can gradually sort of take a underlying mathematical process and decompose it into all these different pieces and understand how they operate, and then sort of model the underlying process of electricity demand or anything else in a way that visually and mathematically it looks right, but it sort of gets us out of the whole issue of having to understand exactly what happens when GDP goes up by 1 percentage point or anything else like that. And so we're going to talk some throughout this lecture about the difference between signal and noise, and this is an illustration of that, right? So by signal, I mean the underlying trend that's visually apparent, and so that would be the top panel here. And noise would be this random process that you could more or less describe as a Monte Carlo simulation, right? That you're randomly sampling from a normal zero mean variance 1 distribution, and there's no autocorrelation, no memory in the system. You're just putting your hand into the hat, pulling something out. That's noise, right? We also call that white noise. And usually processes that we observe in the real world are a mixture of both signal and noise. And so that's what you see on the bottom panel here. You see some clear evidence of this overall clean signal, and that's what we want to take out. But in real life, what we see is that clean signal added with other randomness and uncertainty around it, and that's the noise. So when we're talking about both the signal and the noise, mostly what we're interested in is the signal. But if you're in a utility or you're anybody else making a decision, you have to be able to tell the difference between signal and noise, and often that means accounting for noise explicitly when you're modeling a process to understand. Well, it's just an acknowledgement that whatever model you come up with isn't always going to be perfect. It's never going to be perfect. There's always going to be some random element that your model doesn't predict. And whatever that random leftover element is, we just sort of say, well, that's a random process that we can describe, through a white noise or probability distribution. And so both in terms of the signal and the noise, we describe them very similarly, both in terms of their statistical moments, so the mean and standard deviation of a signal versus a noise, stationarity, right? So whether things change over time, you could have a signal that's very clean, that's stationary, that is a mean, right? A stable mean. But then you could have noise that whose standard deviation changes over time, and that's sort of like the NASDAQ returns we saw, where the mean is the same, but the noise around the mean can increase and become more volatile during certain periods. Seasonality, you could have certain periods of the year where the uncertainty or the noise around electricity demand is higher, and that's definitely true. Autocorrelation, right? So noise and signal can both be autocorrelated, right? So you can have a model that describes an underlying process and then some noise left over, but the degree to which that noise changes might vary, might have some memory in it, right? You could be overestimate 3 periods in a row and then underestimate 3 periods in a row. And so all of this is important for describing both signal and noise. So a big part of time series analysis involves filtering. And so that means changing attributes of a time series and or deconstructing it into its component parts. And there are all sorts of different filters. We're just going to cover a couple here. And the first one is detrending. And so that can mean accounting for a change in mean over time, so a gradual increase or decrease in something. Seasonality, right? So if we recognize that things change on based on some sort of cyclic basis. So if it's weather-based or even economic boom and bust type situations, we can account for that and take out periodic trends. Autocorrelation, right? So we can account for memory in the system, and we're all basically trying to take a signal that's noise, and I mean a time series that has signal and noise, and take all the signal out, all the useful part of stuff that actually is instructive about whatever system we're trying to model. And then we want to leave it so that all there is noise left, and that's something we can just describe via Monte Carlo simulation. Outliers we can also deal with, low pass filters. So that means smoothing, basically. Getting rid of some of the noise in the system and only allowing the really big changes to pass through. So here's an example of what we call non-stationarity, and it's sort of the classic example, which is CO2 concentration. So you may, in other classes, hear the terms climate non-stationarity, and all that means is that whatever mean trend, right, in temperature, precipitation, or anything, we assume to exist based on historical data is not really stationary, right? So the mean is changing. The probability distribution around temperatures in June is changing, right? It's shifting up. Even if the variance around that doesn't change, the mean is. And this is an example of that, where the mean is changing over time of CO2 concentrations. But the oscillations around the mean, the standard deviation and the seasonality here is not changing, but just the linear mean over time. So if we identify a pattern that looks like this, where we think, we could fit a line through this oscillating graph, then we can do that via least squares regression, right? So we can fit, and the model here would be CO2 concentrations is the dependent variable y, is equal to b, which is whatever coefficient we're going to come up with, times whatever the time is, plus maybe a constant c. And that means that given any time and whatever the constant is, which is probably the initial CO2 concentrations, then we can estimate what the concentrations of CO2 in the atmosphere would be in any year, right? And given that model, we can then subtract whatever those CO2, the calculated CO2 values are for each year, and then what we're left with is what we call a detrended CO2 data, or at least detrended in terms of year to year, right? There's still a trend, seasonality trend here, but it's centered around 0, right? Notice that in the right plot, the mean here is 0, right? So we're sort of left with what we might even refer to as errors or residuals in the model, but it's clearly not white noise, right? If we're trying to go from something that a time series process and extract all the signal just so we're left with noise, this is clearly not noise, and the reason is because it is modeled or is centered around 0, and we could easily describe residuals in terms of a probability distribution that's normal, that's centered around 0, but there's autocorrelation, right? The value of CO2 concentrations from one month to the next are very closely related with another, and from one January to the next January, etc. So detrending using a linear model may be useful for making a series stationary. In other cases, that may not work. And so one other option for trying to detrend a time series is to look at differences, right? So the whole idea here is that if the mean, variance, and autocorrelation of the original time series are not constant in time, even after detrending, so taking out this linear trend, it's possible that the statistics of the changes in the time series between period, right, so from period 1 to period 2 and from period 2 to period 3, that those changes will be constant. And so if that's true, then the series is we call it different stationary. And so here's an example of this, and often what we see is that a lot of financial data is different stationary, right? So on the left-hand side, we have the Dow Jones Index. On the y-axis is the index. On the x-axis are the days. And then on the second plot, we have the difference Dow Jones Index. And what that means is that for every point on the left-hand plot, yt, in the right-hand plot, we're saying that value is equal to yt minus 1. So each value in the right-hand plot is really just the difference between two consecutive days of Dow Jones Index data. And so what we clearly go from is something that shows a lot less non-stationarity, right? In particular, what we see is that the mean of the difference Dow Jones Index is constant and roughly around 0. And that's not something we can say for the Dow Jones Index on the left. And so that puts us in a more stationary world for sure. But you can still tell that the volatility or the variance around the mean, even for the difference Dow Jones Index, is not stationary, right? So you still have periods where you have high volatility or lower volatility. In some cases, once we take a difference of a process, we may find that the resulting process, the difference process, has no autocorrelation, right? So the difference from one day to the next is completely random, right? And so this has a very special name. It's called a random walk model, and it's the equation for the random walk model is shown here. It's yt is equal to yt minus 1 plus w, right? And so what that's saying is that the value today is equal to the value yesterday plus some completely the value of some random variable that we can describe completely by a probability distribution, right, with a 0 mean and a variance of whatever, right? And so if we simulate this exact process, starting at point 0 here on this figure, we all start at the same point, right? But each individual simulation, which is a color, the evolution of this value w, we're just reaching into a hat and pulling out a new one, reaching into a hat, pulling out a new one. In some cases, it goes down almost every time. In some cases, it goes up almost every time. And in all other cases, it'll go down and then up and then down. And so anytime where you have a model or a process that you can describe this way, where the way the process evolves over time is completely random, but is dependent on this is not a Monte Carlo simulation. We're not just reaching into a hat because there's memory in the system, right? The value of what we get today does directly depend on the value that we got yesterday. But how we get from yesterday to today what we're adding or subtracting, that is a completely just random variable that is not correlated at all. So the white noise here is not correlated. Lots of time series also display seasonality. So that's, if we're differencing things and taking out linear trends over time, what we may be left with after that are seasonal or periodic fluctuations that we can easily take out. And if it's present, we can incorporate it into a time series model. How do we detect it? One of the easiest ways, and this is something we've done in class, is coming up with box plots. And we're back towards the CO2 concentrations on a monthly basis. But you could think about doing the same thing for wind power generation, solar power production, electricity demand, temperatures, water flows, anything that has to do with the electric power sector often has a lot of seasonality associated with it. So the same way we subtracted the linear process over time to account for the gradual increase in CO2 concentrations, we can also subtract the seasonal or periodic trend from the data, leaving a further detrended process. So what we're starting with now are these residuals that are centered around zero but exhibit really strong seasonality. And what we want to do is get rid of that seasonality and just understand how CO2 concentrations change throughout time if we take out year-to-year trends and we take out seasonal data. What randomness is left in the system? And so we can subtract out the mean monthly concentration after we've linearly detrended things. And then what we're left with at the bottom here is something that looks more like a random walk, right? So certainly centered around zero or close to zero. No seasonality, no obvious periodic behavior, right? So it looks kind of like white noise, except there appears to be maybe some memory left in the system, right? Where if things are below the line, they're below the line for a while. If they're above the line, they're above the line for a while. So the question is this a totally random process? Is this white noise? Can we replicate it just by sampling from a known distribution? And still the answer is no. One of the fundamental differences between many time series, even one that looks kind of like noise, and random sampling or Monte Carlo sampling from a single known distribution, is that time series have memory, right? We just saw this in the case of the random walk. Values in one time period influence values in subsequent time periods. And this, we describe this as, we call it autocorrelation. So autocorrelation, the autocorrelation function, can be used for a couple different purposes. And the first is to detect non-randomness in data. Randomness in data just means you're putting your hand in a hat and you're pulling something out. Even if you can describe data using a probability distribution, if the value of that data from one period to the next are correlated or related, then it's not random. And we can also use the autocorrelation function to help identify time series models if the data are not random, and that's something we're going to do in a future lecture. So I'm going to relate how we think about autocorrelation between values of the same process to how we quantify correlation between two random variables, x and y. So the correlation, we define the correlation between two random variables, x and y, as the covariance between those two variables, which you can describe here, where e is the expected value, and mu here is the mean, over the product of their standard deviations. And so we can boil that down all here. If we have a n sample size of n, we can calculate this by hand, if you wanted to, by taking the sum for each sample n of the value of x minus the mean of x times the value of y minus the mean of y over the square root of the sum of each value of x minus the mean of x squared times the sum of, for each sample, the value of y. And the equation for autocorrelation looks pretty similar, except we're not dealing with two random variables, right? What we're doing is measuring the correlation between a time series and itself, really, at different lags or shifts in time. So let's say we have this time series y, right? And so we have y1, y2, all the way up to yn at time 1, time 2, all the way up to time 2. The autocorrelation for a lag of k, right here, the autocorrelation for a lag k looks kind of similar, right? So you're taking the sum for each sample you have between y at time period I minus the mean of y times the y at time period I plus k here, right? So the same variable, we're just like looking into the future and trying to figure out the correlation between this and this, basically, right? And then we're dividing by the sum of yi minus the mean of y squared. And so, for example, if we're looking at the correlation of two random variables, we might be looking at the correlation between x and y here. And if we're looking at the autocorrelation, we're looking at the correlation between this process y and really the same process, but this is shifted by k periods, right? So you can think about this point being related to this point and this point being related to this point. But mathematically, we're basically treating them as separate processes, but that's all we're doing. We're shifting the time series in time and then taking the correlation of that shifted time series with itself, basically. And what that tells us, if you had a really high correlation between a time period and itself, every 10 time periods, that would give us some idea of periodicity, right? So like every 10 time periods, the correlation increases. That means something happens that's sort of unique every 10 time periods. Every 10 time periods, something happens that makes the value about the same every time. In other cases, we might not see any periodicity at all, but what it might just give us an idea of is how long certain values can sort of persist in the memory of a system. So if we come up with this value of autocorrelation here, and this is the correlation given a k lag, right? So k is on the x-axis. And we have 0 here, and 1, and then maybe 2, and then maybe it goes all the way out to 24. So what this tells us is that for any given process, or the process that we're modeling, this tells us the degree to which the correlation between two different points changes as a function of how far apart in time they are, right? So that means that when you have any 2 points, it could be time period 3 and 4, time period 5 and 6, time period 9 and 10, this all gets included in this value here, the correlation at lag 1. So no matter where you are in time, the difference between 2 consecutive time periods, the correlation is very high. But the further you get out here, like let's say here, that means the correlation between time period 1 and 3, and 2 and 4, and 3 and 5, and 4 and 6 is considerably lower, right? So, and you can keep going further out here until basically you get to a point where if you're far enough away in time, you could actually start to consider the two values of the same process to be statistically independent. So if we eliminate all signal elements of of signal here. We get rid of the trends, we get rid of the periodicity, and then we get rid of autocorrelation. What are we left with? White noise, right? So a white noise is a completely random process whose samples are regarded as a sequence of serially uncorrelated, so no autocorrelation, random variables with zero mean and finite variance. That means that we can perfectly, finally replicate a white noise variable by simply randomly sampling via Monte Carlo simulation from an appropriate statistical distribution with replacement, right? So if we've gotten rid of all these signals, the trends, periodicity, and autocorrelation, all we have left is some sort of random variable like this, then we can directly sample it from it and get the leftover time series process. So something else we can do with time series filtering is smoothing. And so what this does is it removes or reduces the importance of really high frequency spectral components. So changes in the time series that happen day to day, so noise basically, we get rid of that stuff, and what we're left with are just the really important parts of the data that have been passed through what we call a low pass filter, because the changes that happen at a lower frequency or more gradual changes do come through the filter, but all the little noise around that main signal are removed. And there's a bunch of different types of filters you can use, and they all have sort of different usefulness in different situations. A statistical filter is where you're weighting consecutive values through this sort of kernel that you move consecutively through a time series. So for example, in table 1 here you have 9 years of data, and your filter is taking 3 values at a time, and it's outputting a single value that is the sum of 25% of the first one you're looking at, 50% of the second one you're looking at, and 25% of the third one you're looking at. So in this case, you're taking, if the filter is centered around year 2, 3, and 4, it's inputting the time series value 17, 10, and 22, and it's outputting the sum of 0.25 times 17, 0.50 times 10, and 0.25 times 22. And you end up with the value, or you should end up with the value, 1475. Actually, I'm not sure which one of those it's going to end up giving you. I think it should be 1475, but you can verify. And how we use those filters can vary quite a bit, right? So you can have a linear decay, so that if the position of the filter is centered around one value in the time series, then the weights that you assign the time series values on either side of that can decay linearly, or we can take just a simple moving average, so that whatever values we're looking at in the filter all have the same weight. Okay, here is a useful thing to remember when you're smoothing, especially when you're coding. This can end up, if you're not looking out for this, as sort of a weird issue. By definition, when you're smoothing, you're going to lose data, right? Because when you're smoothing something and you're passing it through this filter, you're combining multiple values and you're outputting a single value, right? So if you're doing a central moving average smoothing filter, right? You're taking 3 values at a time and taking the average of them, and then you're outputting 1, right? So if you start a time series and you're looking at periods 1, 2, and 3, and you take the average of those, and then the smoothed value is the first data point of your new filtered time series. It works right at the beginning, but when you get to the end of the time series, you're going to be trying to filter the last 3 values, and then the last two values plus nothing, and the last value plus two nothings, right? And so inevitably you're going to lose data on either end of your time series. And how you deal with that, whether you're going to replace it or just ignore it, depends on the problem you're trying to answer. So the end result, this is the end result of the exponential smoothing. And so again, why do we do this? And the answer is really to take out all the high frequency spectral stuff and leave in the really important trends. Like if we know what is important and we want to just focus on that, this is a way to bring that out, sort of like detrending the data. Whether you're extracting a linear trend or periodic trend, this is another way of getting rid of the noise and taking out the signal. And here's an example of that. So you have on the y-axis here the relative variance, and on the x-axis here the frequency, right? And so the variance gives you an idea of what overall is driving the dynamics of the process, right? And so what we want to see are that we retain high amplitude events that don't occur very often, right? And we want to get rid of events that occur pretty frequently. And so on the x-axis here is the frequency. So all the way on the left are things that don't occur very often, and as the frequency increases, it's stuff that happens more frequently. And so you can see the difference between the original time series and the filtered time series. What we're left with in the filtered time series are low frequency events, so longer duration, more gradual changes that really are important for driving the system. And you can tell we lose some information, right? We lose some amplitude here, but we do have this advantage of getting rid of all the other stuff, basically above a frequency of 0.1, that just gets completely removed from the signal. And it makes it a lot easier to evaluate and to describe without potentially risking, making an assessment that includes some risk or tries to describe the time series in a way that gives a little too much importance to these random events that happen around the signal we're actually caring about. Okay, so that's the end of this one. The itlnist.gov handbook is a really useful resource if you're ever thinking about engineering statistics, time series analysis, or anything like that. So I would really encourage you to check that out if you have any questions. Okay, thanks.